All right, our next lesson is actually an application of proportion. So we're in unit or lesson 5.6. We're on your notes packet, pages 10 and 11, and we're going to be talking about similar figures today. We're going to start off with a couple definitions here. Similar figures have the same shape, but are not necessarily the same size. If you have two polygons or two shapes that are similar polygons, their corresponding angles are congruent, and the lengths of the corresponding sides are going to be proportional. So you can see where our proportion comes in. Corresponding is a word that you saw a couple times in here. It means that they are located in the same spot. And the word congruent means that they have equal measures. So when we look at the first example that's down here, we have two triangles that are similar to each other. Triangle ABC is similar to DEF. And you notice that we can write that with this little squiggly line in between. So if you see that, that tells you they are similar. They're the same shape, but different sizes here. So what we look at is we have AB is this side over here, and AB comes first when we actually name the triangle here. It's going to correspond to the first two letters on the other, which is right over here, side DE. Similarly, we can have EF, which is over on this one, which is also the second two letters, corresponds to the second two letters, or BC, on the other triangle. So EF corresponds to BC. Those sides would actually be able to make a proportion then. We can compare AB to DE and set that equal to BC over EF then. A couple other pieces to talk about when we look at angles. Angle B is congruent to angle E because they're located in the same spot. I should put a little angle mark there. We also have angle D, which is up here, is going to be congruent to angle A because they're in the same spots as well. This little equal sign with the squiggle on top, that's your symbol for congruent. So the second part of this, we need to use proportions to find the values of X and Y on here. So we said we could take this blue side and compare the 3 to the 15 as a ratio, and then we could compare that with the two yellow sides, the 4 to the Y. One thing I will do here is I will actually circle the 3 and the 15. I'm going to box up the 4 and the Y, and then I'm going to actually just put like a little triangle around the X and the 35. Those are the sides that are in the same spot. They're corresponding here. So what I'm going to do is I actually need to look for a pair that has numbers in both spots. So looking here, I have an X with the triangle, I have a Y with the box. So I'm looking at this 3 and the 15. They are going to make up the first part of my proportion on both of my proportions for finding X and Y. I want to include what's given to me instead of using what I figure out. So if I wrote this with the 3 on the top and the 15 on the bottom, that tells me when I go to find my X one, I'm going to have to put X on the top and the 35 over here down on the bottom because they're corresponding, and I have to follow that same pattern. So X over the 35 then. When I set up my proportion for the Y, I'm going to do the same thing. Since I put the 3 on top, I need to put the 4 on the top of the other side of my proportion. And since I put that 15 on the bottom, the Y is going to have to go on the bottom of my proportion. Now that I've set them up, I can just go ahead and solve these. So if I do 3 times 35, I get 105. 15 times X gives me 15X. To get X by itself, I'm going to divide by 15, which is going to give me 7 equals X. Over here, I'm going to do 3 times Y, which is 3Y. 15 times 4 is 60. And divide by 3, and we get Y equals 20. So we figured out that 7 is X and Y is 20. And you probably noticed that there was a pattern, and with this being 3 and that being 15, to go from the smaller triangle to the bigger triangle, we can multiply by a factor of 5. So anytime you're looking at differences in their sides, you're going to be multiplying by factors here. In example 2, you have trapezoid ABCD, similar to trapezoid EFGH. So we're going to go through. I see a 5, and I see the Y plus 4 is in the same spot. I see the 2x, and I see the x plus 12 are in the same spot. And finally, I see the 24 and the 48. Again, like before, we are going to look for which one has numbers in both sets, and that would be the triangles here. So I'm going to set this one up where these pieces are going to go on the top and these pieces are going to go on the bottom. So in both of my proportions, because I'm looking for x and y, I'm going to start out with the knowns, the 24 over the 48. I'm going to do x first, so that means I'm using 2x on the top for this side, and the 2x is in the same spot as the x plus 12. I'm going to go ahead and actually set up the other proportion too. So we have the 5 goes with the y plus 4. So the 5 is from the trapezoid for the top, and the y plus 4 is from the trapezoid for the bottom. I'm going to go ahead and solve these. Again, this is an expression, so I have 24 parentheses x plus 12. 48 times 2x, I'm going to do the 48 times the 2, which gives me 96 times x. Since this is a little bit more complicated with an x, not just a plain number, I'm going to go ahead and actually distribute here. So 24 times 12 then will give me plus 288 equals 96x. I'm going to move my 24x. So we have 288, and 96 minus 24 is going to give me 72x. We're going to divide by 72 on both sides. And 288 divided by 72, we get 4 equals x. For my other one, I'm going to put this expression in parentheses. So I have 24 parentheses y plus 4. On the other side, I get to do 48 times 5, which is 240. Because this is a plain number over here, I can actually use that shortcut and divide by 24 instead of having to distribute and then take care of everything. So 240 divided by 24 is 10. I'm going to subtract the 4 on both sides, and I get y equals 6. So that's all great and nice, but if we go back up here, x is 4. That still doesn't tell me how long this side is, so I do need to plug it in. So 2 times x, 2 times 4, which is going to give me 8. X plus 12 would be 4 plus 12, which is going to give me 16. Same idea with the y. I have y is 6. So y plus 4, that's going to be 6 plus 4, which is actually going to be 10. So then down here, there's a couple questions. Side BC is right here, the side labeled 2x, which we just found out was actually equal to 8. Side FG is over here on the right side, which we just did x plus 12. 4 plus 12 is 16. And finally, for side EH, it's going to be over here on the left side of this one. We just found out by plugging in for y that side is going to be 10. For your last example here, you have 2 triangles. We have triangle ABC is similar to ADE. You'll notice that the little triangle is inside the larger one, so we actually call these nested triangles. When you have nested triangles, I would recommend that you actually re-sketch them real quick. So here's the little one, and here's the bigger one. So for the little ones, I have sides 3, 4, and 5. For the bigger one, I have y, 12.5, and then down here I have x. So the 3 side goes with the y side, the 5 side goes with the 12.5 side, and the 4 goes with the x. That 5 and 12.5 both have my numbers, so I'm going to make this to be my top and this to be my bottom. So I'm going to start off 5 over 12.5 and 5 over 12.5 because I'm solving for x and y. We'll do x first. So I notice that x is right here and it goes with the 4. This 4 is the one from the top though, so I'm going to put 4 over x. And I'm going to also go ahead and set up for my y. The y is in the same spot as the 3. The 3 goes on the top and the y goes on the bottom. So solving here, x times 5 is 5x. 12.5 times 4 is going to give us 50. So when we divide by 5, we get x equals 10. For the other one over here, we get 5y. 3 times 12.5 is 37.5. And we're going to divide by 5. And we get y is equal to 7.5. So those are our missing values for x and y here. That's how you would handle a nested triangle with setting it up for similar figures.